Hello, thank you for joining me. I want us to look at the concept of binding energy of a nucleus. Now, we all know that yes, the nucleus has the nucleus of an atom has two particles in it, and those two particles are the neutron and the proton. Now, these two particles are held together by a particular force. And then, of course, the same energy that holds these two particles together is still the same quantity of energy that is required to break it. In other words, we can now say that binding energy of a nucleus is that quantity of energy that must be put into the nucleus of an article or a particle in order to break it into its constituent particles. Or we can say that the binding energy of a nucleus is that minimum energy required to separate the nucleons together. So those nucleons that are bound together, the minimum energy required to separate them completely is what we refer to as binding energy. Now, this binding energy can as well be written as, you can either say binding energy or you can say have it as ordinary E. Most books use ordinary E. So if we want to use ordinary E, we can still have that, yes, binding energy is proportional to the difference in the masses of these particles of the nucleus. Now, the mass is there. We have the mass of the particle, total mass. So we can say total mass of particle. Total mass of particle minus mass of the nucleus itself. Mass of the nucleus. Mass of the nucleus. Now, this mass of the particles there, just like we said earlier, are the neutrons and the protons. So in other words, we can now say that yes, binding energy is total mass of the particle. That the total mass of the particle are, we have ZMP plus NMN. This is for the particle. Minus, we have the mass of particles there. The mass of particle AZ put together. So this is the mass of the particle. The particle will have and then this is the mass of the nucleus. Where Z is the number of protons. Number of protons. And itself is a number of neutrons. Number of neutrons. Now NP is the mass of protons, while Mn is the mass of neutrons. Mass of neutrons. Why just this one is the mass of the nucleus? Any nucleus given to you, they will give you the mass, or they might ask you to get this in order so that we can get this. So we now have that, yes, M into AZ is mass of the nucleus. Any atom given to you, the nucleus will be given to you. Now we can now have that all of this is measured in joules. Most times they can give you this mass to be in atomic mass unit. Atomic mass unit or unified atomic mass, U. Now U is 931 mega electron volts most times. So this is, you might be given this. Also, the energy released during energy release. This one is one of the equations. We can still use this one during radioactive decay. The energy release is this. Or we can still have the one that says energy released is equal to delta mc squared. Now this is called Einstein's equation. Einstein's equation of energy. Einstein's equation. Now where m is difference, mass difference, then c is the speed of light or velocity of electromagnetic wave. Most times it is always given. Okay. Now the first question is calculate in joules the binding energy for lithium 73. Now these are the values given to us, still down below. Atomic mass of lithium 73 is 7.01600 atomic mass units. Mass of proton is this, mass of neutron is this. Now unified atomic mass U is this, and then 1 electron volt is this. Now because you were asked to calculate the binding energy in joules, that is why we are given all these values. Now all we need to do is solution. Apply our formula first. Before the formula, we now have the atom, the element in question is lithium 73. Now from here, we know that number of this 3 here is the number of proton. So we now have Z is equal to 3. Now M from the formula ZM will give us, which is number of proton times mass of proton, which will give us 3 times mass of the proton. Mass of the proton is 1.00783 U. Now N is, and of course from here, this 7 here is made up of the neutron and the proton. So here we now have that 7 minus 3. Whatever that is remaining is the neutron, which is 4. Therefore, neutron is 4. We now have NMN will give us 4 times mass of neutron. And mass of neutron is 1.00867 U. Having done this, remember our formula. So all we need to do is the one that says binding energy is ZNP plus NMN. So all we need to do is add. So if we add these two, if we add it together, it will give us, sorry, we have not even multiplied, sorry. We have not multiplied. All we need to do is we multiply these values. So if we multiply them, we have 3 times 1.00783 will give us 3.02349 U. This one will give us 4 times 1.00867 will give us 4.03468 U. Now we add the two together. So if we add the two together, we'll now have 7.0. Something will give us 7.05817 U. Now this is a mass of individual particles. Now we now come back here and say from the equation that says E is equal to ZNP plus NMN minus mass of individual particles. Sorry, mass of the nucleus. So this one is this. So this one, mass of this nucleus is this one given to us. which this 7.006. So well, the next step is to bring our mass defect. So of course what we now have now is the mass defect or mass difference, which is change in mass. Change in mass. Mass of proton and neutron put together will give us this 7.05817 U minus mass of the nucleus. Mass of the nucleus was given to us to be 7.01600 U. If we subtract the two, our mass defect will give us 7.05817 minus 7.01600. Will give our mass defect will give us 0.004217. Now at this point, we now have this, there is U here. So this is a mass defect. This is a most, be careful. They may, in questions, if it's OBJ, they may stop here. But if they did not stop here, put in the value of U. When we now put in the value of U, that will now give us our binding energy, which is mass defect times this 0.04217. Now we put the value of U. U was given to us to be 931 mega. Mega means times 10 raised to power 6 times electron volt given to us. 1 electron volt is given to us to be 1.6 times 10 raised to power minus 19. So which will give us that E is equal to the whole of this times this times this. Let me take the basis first. 931 times 1.6 will give us, down here will now give us 6.62.8164 times 10 raised to power. Now when I have this one will now give us 6 minus 19, and 6 minus 19 will give us 6 minus 19 will go minus 13. So when I got it's raised to power minus 13. So this is our final answer. We put this in standard form, which will now give us 6.28164 times 10 raised to power minus 12 joules. So this is our answer. So in exam, be on the lookout. Then they stop here. So if they stop here, you stop here and put U. If they continue up to joule, you continue up to joule. But from the question, they say calculate in joules the binding energy for lithium this. So this is our final answer. We take the second question. The second question says the atomic mass of potassium 3919 is 39.00 atomic mass units. We have here mass of proton, mass of neutron, and then value of one atomic mass unit. Now the first question says here, number 1, calculate the sum of the masses of the components, particles of the nucleus. Second one, mass defect. Third one, binding energy. Now we'll take them one after the other. The first one is sum of the masses. So now sum here now is we have potassium 3919. Now from here we now know that this is proton. Number of proton here Z is 19. Now we have the ZMP, which is number of proton times mass of proton. Mass of proton is this. So we now have 19 times 1.00759 U. N, which is number of neutron. Whatever is, so 39 minus this will give us neutron, which is 20. So number of neutron is 20. Now NMN, please. That is number of neutron times mass of neutron will give us 20 times mass of neutron. Mass of neutron is 1.00898 U. Okay, which will give us, by calculation, it will give us the first one, 19 times 1.00759 will give us 19.14421 U. Second one, 20 times, which is a mass of the proton, mass of neutron, will give us 20 times 1.00898, which will give us 20.1796 U. So sum of the individual masses of the particle, which is this. So once we sum, we add the two together. We now have bring U here. 1 plus 6 will give us 7. This one will give us 11. Right one, carry 1. Bring it here. This one will give us 7 plus 9 is 11. 11 plus 1, 12. Carry 1. Bring it here. 5 plus 1, 6. Now bring down 1 here. So 19 minus 20 will give us 1. So we have this. So let us still check it. Plus, sorry, this is sorry. Sorry. This will give us 39, please. 39. So 20 plus 19.14421. We got 39.3981, please. Bear with me. It's 9.32381. We will add this two together. So it will now give us, this is the sum of individual masses. Now the second question says mass defect. Mass defect. Mass defect, which is the mass difference. Delta M is equal to mass of individual particles minus mass of the nucleon. So this is the mass of the nucleus. So this is mass of the nucleon. Now I have 39.32381 minus 39.00 all in U, which will give us that delta M is equal to 0.32381 U. So this is our mass difference. Now the binding energy, with binding energy II, binding energy E will give us, we now put in the value of this, that is the difference. So we now have 0.32381 times U. Now we come up here, we're given the value of U. U is 931 mega electron volts. So this mega times 10 raised to power 6 electron volts. Or you can just write 931 MeV if you don't want to put the value of this. So that means if you put the value of this, the remaining answer will now be in electron volts. So if we multiply this by 931, we will now have 301.46 times 10 raised to power 6, which will give us 3.0146 times 10 raised to power. Now, if you shift this, we now have times 10 raised to power 8 electron volts. Or here, or we just have here, once we come to this place, we'll put 931 here. So if we put 931 here, multiply this thing by 931, it will give us 301.147 times 17 mega electron volts. Either you have it like this or you have it like this. This index number here is as a result of this mega. That is why we have this index number and the electron volt, or we just have 301.147 mega electron volts. So the answer will now be in, this one is in NEV, this one is in EV. So that's the difference. Okay, we still take another question. This one says mass of proton is 1.0074 U and that of neutron is 1.0089 U. Determine the energy involved in stabilizing the nucleus of nitrogen of mass number 14 with 7 protons and 7 neutrons. Now we're given that the speed of light is 3 times 10 raised to the power 8 meters per second, and 1 electron volt is given to be 1.67 times, sorry, 1 atomic mass unit is 1.67 times 10 raised to the power minus 27 kg. So we take them one after the other. So we now have that here, it is nitrogen. Now they said this nitrogen 14.7 here is 7. The mass number of this nitrogen 14, this is this. Now we have that mass of neutron and mass of proton. So mass of the proton is 1.0074 U, and that of neutron is 1.0089 U. So we want to find the energy involved. Now C is 3 times 10 to the power 8 meters per second. 1 U is 1.67 times 10 to the power minus 27 kg. Now this one is this mass. We have, this is the mass of the nucleus. Okay, so we have this. So this is the mass of the nucleus is 14. That is 1 U, please. So we now have, from what we have on the board, Z is 7. Now ZMP will give us 7 times mass of proton, 1.0074 U, which is equal to, we'll get that later. Now from here, N, of course, 14 minus 7 is 7. So which will now give us that NMN will give us number of proton is 7 times mass of neutron, please, 1.0089 U. Now let us calculate them out. So which will now give us 7 times 1.0074 will give us 7.0518 U. This one will now, mass of the neutron, 7 times 1.0089 will give us 7.0623 U. Now, and of course, we add the 2. If we add the 2, we'll have U here. 8 plus 3 will give us 11. Right one, carry 1. Bring it here, 2. 2 plus 2, 4. 5 plus 6, 11. Carry 1. Bring it here, 1 point. This 14. Now, mass defects. After adding, the next thing is mass defect, delta M. Delta M is mass of the particle minus mass of the nucleus, which is 14.1141 U minus 14. Of course, there should be U here. Even if they did not put it, we'll put it here. U which will now give, if we subtract this from this, to give us 0.1141 U. Okay, so this is our atomic mass, our mass defect. Now, the energy released at this point, we convert, because the next thing is to, in fact, we convert it, because we are going to use energy release is equal to m delta mc squared. So because this one is in this, that is why they gave us this, that we can now convert it to mass. Once we convert it to mass, which is in kg, we can now multiply it by this. So in conversion, similarly, mass defect delta m is equal to 0.1141 times U. U is 1.67 times 10 raised to the power minus 27 kg. So we now have 0.1141 times 1.67. There is 7. Okay, which will give us that delta m is 0.19055 times 10 raised to the power minus 27. Therefore, if we put this in standard form, it will now give, this one will reduce, this one will have this. So we now have delta m is equal to 1.9055 times 10 raised to the power minus 28 kilogram. At this point, we now use the Einstein's equation. If we use this, all we need to do, we have this already. All we need to do is to bring in C. C is given to us, so we'll bring it in. So we now have that E is equal to delta M. Delta M is 1.9055 times 10 raised to the power minus 28 times to 1.9055 times 10 raised to the power minus 28 multiplied by, now from the law of indices, we square this and multiply this one by 2. If we square this, we now have 9 times 10 raised to the power. This one will now give us 16. So which will give us that the binding energy is equal to, now we multiply the base. If we multiply the bases, we have 1.9055 times 9 will give us 17.1495 times 10 raised to the power. And we now add the index numbers. Minus 28 plus 16. Minus 28 plus 16 will give us minus 12. Therefore, we can now conclude that the binding energy, if we put this in the standard form, we now have 1.7 times 1.71495 times 10 raised to the power minus 11 joules. So this is our answer in joules. So if because of this, they say calculate it in joule. They gave us all these things. The energy released now is in joules. So we'll take the next question. Question says, a substance of mass 2 times 10 raised to the power minus 5 kg undergoes a fission process which decreases its mass by 0.3%. What amount of energy is released? I'll repeat. What amount of energy is released in the process? Given that speed of light is 3 times 10 raised to the power 8 meters per second. Okay. Now this one says the mass of the substance is given to be 2 times 10 raised to the power minus 5 kg. Now it undergoes fission process, and the mass decreases. This mass is decreased by 0.3%. 0.3%. Now, what amount of energy is released in the process? So, the energy released in the process, and of course, the energy released in the process is binding energy. And this binding energy E is delta mc squared, or mc squared, as the case may be. Now, the only thing we have now is this. This is the mass, this is the initial mass. So at the end of the day, it was reduced by this. So what we need to do now is to find the 0.3% of this. So therefore, mass will give us 0.3% of this one will now give us 0.3. And of course, put it in percentage is over 100 times this mass. This mass is 2 times 10 raised to the power minus 5. Therefore, mass will give us, from our calculator, we now have 0.3 divided by 100. They are multiplied by 0.00. Okay, everything will now give us 6 times 10 raised to the power minus 8 kg. So this is what this one will now give us. Now, energy release is m delta mc squared, which will now give us that 6.0 times 10 raised to the power minus 8 times c. C is 3 times 10 raised to the power 8. Remember, it is squared. Since it is squared, we now have 6 times 10 raised to the power minus 8 times this one. If we square this one is 9. This one is raised to the power 16. 9 times 10 raised to the power 16. So, which will now give us, by calculation, 6 times 9 will give us 54. Energy is 54 times 10 raised to the power minus 8 plus 16 will give us positive 8. Therefore, the energy released in the process is 5.4 times 10 raised to the power 9 joules. That is the energy released in the process when this particular mass decreases by 0.3%. Okay. The last but not the least, we'll take this one, and possibly this one to show that you really understood this. Please do this one and then give me the answer in the comment section. And this one says the amount of energy released when 0.5 kg of uranium is burnt completely is dash. The amount of energy released when 0.5 kg of uranium is burnt completely is option A, B, C, D. Tell me which of the options down below is the correct answer. This is where we'll bring the lesson to an end. If you have not subscribed to this channel, do well to hit the subscribe button, turn on your notification bell so that anytime a new content is uploaded, you will get notified. Please do well to share this video with your friends. Thank you.